Okay, hello everyone. Welcome to the Quantum Physics seminar today. So as a reminder, our seminar runs every month. It's the second Tuesday of every month. And then in SFU, we will have an in-person, always in-person room booked it with a coffee and temperature served. So please come to the in-person. So today it is my honor to have Professor Paul Haljan from the Department of Physics from Simon Fraser University to give us a talk. So Paul did his PhD in University of Colorado at Boulder and also in Gila. And after that, he went to be a postdoc in Michigan with Chris Monroe. So if you recognize names, during the time they worked a lot on quantum trap-line quantum computer technology, and that's laid the foundation of the recently pretty famous quantum computing company IonQ. And after the postdoc, Paul moved back to Canada, and then he started his own group in Simon Fraser University. His group is mainly focusing on developing the technology to build quantum trap-line quantum computer, as well as using trap-line devices to do quantum computing, quantum technology, and quantum simulation, and other kinds of quantum technologies. So today, I think he'll be telling us more about his recent work in quantum phase transition with a trap-line motional state. So Paul, thank you. I think I do. Yeah, yes.
All right, thank you. First, just checking that I can be heard. Does everything sound pretty good? All right, good. So welcome to all of you here locally. Nice to see some familiar faces. I can't see the folks in UBC, but I'm waving. And thanks to all those who've come via Zoom to the talk. All right, so I'm going to let's just start here. I'll just start with just a quick overview slide of my research group. So here at SFU, I'm an experimentalist, atomic physics experimentalist, focusing on ion trap technology. So building experiments based on ytterbium ions, controlling them with lasers down at the quantum limit of their behavior. So I have a number of projects that going on in my group. I'm going to tell you about focus on one today. So we do a range of quantum technology development that's evolving currently into some more quantum computing specific focused work. However, the work that I want to tell you about today is really more like a quantum simulation. We've been focusing actually for a number of years on developing the technology, theoretical tools as well, to realize and understand a quantum phase transition in a string of ions. So it really is quantum state engineering. In many ways, in many cases, we're pushing the limits of the ion trap technology to see this. I'll talk about that. And then at the end, I want to tell you a little bit about so an application that we're thinking of in terms of quantum sensing of electric field noise in ion traps that has some quantum computing application, I think. So in the spirit of a quantum seminar in the summer, so I thought I'd introduce a little bit of the hardware of trapped ions, so particularly in the context of quantum computing. So just for the first few slides, just give you a little introduction to trapped ion hardware. So when you have charged particles, there's a number of ways to trap them. In terms of quantum computing, particularly the dominant type of trap used is what's called the linear RF Paul trap. And so you can see a very simple example of it here. So essentially you have 4 rods, and we're applying both radio frequency and DC voltage in order to trap. In red there, you see a string of ions. So the RF is actually applied, and that's what you see on the right there, to generate a quadrupole in the transverse direction. You can see, just like water, It's really the reason is the divergenceless nature of the fields. You see electric fields coming in, but then they come out. So by itself, you just had a quadrupole like that, you can't trap charged particle. The secret here is that these are oscillating fields. And interestingly, on average, as the field oscillates, going between confined and unconfined along the two directions, if you choose the frequency just right, depending on the charge and mass of your ions, you can realize confinement. So in what's called a pseudo potential. So, and it's pretty simple typically for these traps. It's a harmonic trap by and large. So here's an example actually of a trap in my group. So we use, it's called a 4-rod linear Paul trap. You can see 4 rods, its typical size is half a millimeter. You can see 2 end cap needles with some DC. Typical frequencies, this really is radio frequency technology, 30 megahertz. Hundreds of volts. We're also applying DC voltages from 1 to 100 volts, and we achieve strong confinement. Also deep trap depths, but the confinement are on the order of megahertz. So that's significantly stronger than, say, a typical optical lattice trap if you're familiar with neutral atoms. The traps are quite deep as well. So, you know, one volt, 1 EV, 10 to the 4 Kelvin. These traps, ultra low vacuum, even if there's collisions with some residual background gas, will hold an ion trapped for a long time unless there's charge exchange and it becomes neutral. So these strings that you see below, this is 40 to 50 ytterbium ions. Been laser cooled to be cold enough that the Coulomb interactions dominate and they form a crystal. So this would be something like a qubit register for trapped ions. These crystals will remain trapped for hours to days. So you have a smaller number of ions, there's less probability of events to happen, so they last longer. But these crystals, you know, we do experiments with the same crystal over the course of hours or a full day. So this is done in UHV, so ultra high vacuum. It is done at room temperature, although modern traps have evolved towards also cryogenic type setups. So that's what's called a 3D trap. They're relatively easy to construct. But I just wanted to bring this in terms of if you're familiar with seeing some of the technology from different commercial enterprises building trapped ion quantum computers, are using trapped ion or surface ion traps. This is where you take, as you can see over on the left side there, a 3D electrode structure and really just deform it onto a surface. But the point is, it's the same idea. So you still have a RF pseudo potential. Here you have the ions essentially floating above the surface, 100 microns or so. And the advantage here is these can be microfabricated, and you can think about integrating both optics or even electronics. And so you see some examples over here. So the bottom one, say, is from Honeywell, now known as Quantinium. But it's the same idea. Okay, so that's essentially trapping ions. So let me tell you a little bit about the ions themselves. So we use ytterbium ions. So singly charged, and they have a particularly simple energy level structure, at least near the ground state. So for storing quantum information or manipulating quantum behavior, for my lab anyway, we focus on what are called hyperfine qubits. So in the bottom of the picture there, you see the ground state hyperfine structure of the ytterbium ion. So it has nuclear spin 1/2, so it has very simple hyperfine structure. And any two of those states can form a qubit. We choose a 0, 0 and 1, 0. So that's F equals 0, total angular momentum, and MF equals 0 or 1. MF equals 0, in both cases, that's projection angular momentum. Because these states are lowest order, are almost insensitive to magnetic fields, close to zero magnetic field. So that makes them very robust to magnetic field fluctuations from the environment. So that's storing of the quantum information in a qubit. In terms of reading out a superposition or reading out whether you're in, down, or up spin state, we use optics. So we have a laser resonant transition that is resonant, for example, with the upper state to an excited state on an optical transition at 369, so near UV. We collect the fluorescence, and this fluorescence detection in about 10 photon counts. From 10 photon counts in about 400 microsecond, we can detect what we call a bright state, so spin up. So you can distinguish that from spin down because the transition here is off resonance. So, and that's actually due to the fact that you have this very large 12 gigahertz splitting between the 2 qubit levels. And so you see a picture from my lab. We can distinguish dark and bright with some limitations due to errors. In this version of the picture you see here, giving fidelities in single shot of 97% if you put a discriminator between those two distributions. So just to compare, so just to give you a general overall picture, 97% is certainly not where this can be limited. You can reach fault tolerant thresholds for detection in short amounts of time, 10 microseconds, for example, Duke and calcium, they've achieved even higher fidelities. So ions, the readout is relatively easy actually, and to get very high fidelity. So let's talk about quantum operations. So the first one I want to talk about actually is spin flips, so coherent spin flips. So how do you flip from down to up? Or perhaps have a superposition in between? We use what are called stimulated 2-photon Raman transitions. So we use lasers because you can focus them to get individual addressing. I have a picture over here of two beams, Raman beam 1, Raman beam 2. Raman beam 1 is big, so it covers all the ions, but you can have one that is focused down such that the combined interaction only happens on individual ions of choice. And then you can imagine shifting that focus around to get full individual addressing. These two lasers together, if they are, as you see in the picture there, off resonant from that excited state, you don't actually undergo a direct transition, but the combined two transitions together via what we call a virtual state will drive a spin flip transition from down to up. And the coherent coupling rate depends on the powers in two lasers, as well as that intermediate state detuning. So the fidelities of this can be quite high. So example in my group, without much trouble, in 10 microseconds, you get 95% fidelity. If you push these things, you can get faster, but you can also achieve four nines of fidelity for these single qubit operations in this way. It's also possible actually to use microwaves just to direct couple, but it's harder to get individual addressing with microwaves just because the wavelength is so big. Okay, so the last little piece of the puzzle here is to talk about engineering entanglement between the ions. And so I'm thinking about the qubit states here, these two spin states. I'd like to entangle the spins of individual ions in a string. So the way that you do this, and I'm only going to want to give you a feeling, so a semi-quantitative feeling, without going into too much of the detail. So I have this picture up above, string a register of ions and I want to entangle a pair of them, I can use optical dipole forces from laser beams focused to, say, a chosen pair to induce essentially dipole in the individual ions. And those two dipoles will interact by a dipole-dipole coupling, which you see there, because it's 1 over r cubed. So the key here, though, is that I can make those forces, those dipole forces, spin dependent using polarization of the light. And so with spin dependent forces, I can take this effective dipole-dipole coupling that comes from the charges and turn that into a spin-spin interaction. So that's the second line there, where the J is really includes all of the details that I just mentioned. So a spin-spin interaction, that's an entangling gate actually between a pair of ions. So if you apply that for a certain amount of time, you have a unitary operation that realizes what's called Mulmer-Sorensen gate. So if you arrange to do this in the X spin basis, that's particularly the Mulmer-Sorensen gate, although you can do it in any particular basis. And this is the favored gate for quantum technologies with trapped ions, so is implemented commercially, for example. So it has a number of advantages. So one thing that I want to bring up, though, is it's actually more complicated than what I showed you there. So the dynamics that you actually perform in this case, or the gate that you perform, is really a dynamical process. So the picture that I showed you is almost like a DC picture where you saw two dipoles. So you take, in order to make these gates quick, actually, you take advantage of the fact that you can drive the motion of ions with these spin-dependent forces resonantly by coupling to different modes. So for example, you see a center of mass mode there. So I'll show you a bunch of these modes in a second. But so this goes back to the original implementation, or the original concept of trapped ion quantum computing by Straxaller in 1995. Although you see a macroscopic motion there, you should really imagine that we can cool these to the ground state, actually. And in that context, these are really these are quantized modes, so sometimes called Q modes. And so you see the little picture there, it's a harmonic oscillator. These are in the linearized regime. And so you can start in ground state, first excited state, for example, could form a qubit of their own. So these modes are actually called quantum data buses, because it's the coupling of the ions to these modes that allows for the effective spin-spin interaction. So these spin-dependent forces that I was telling you about, the way that we actually think about them more technically is they're Raman transitions, but more complicated than the ones that I told you about before, where we flip the spin. This two-photon transition can not only flip the spin, but it can also change the motion. So you see, for example, go from n equals 0 to n equal 1. So we're not only are we changing the spin, we're changing the motion simultaneously. We're actually entangling them. And so in this resonant process, you transiently actually entangle the spin with the motion. You undergo some dynamics at the end of it, the end of the gate. You disentangle the motion from the spin, and you leave the two spins entangled. That's the way it actually works. So when you have a set of ions, so 4, for example, you actually have a whole set of modes. And so this just shows you, so if you have 4 ions in 3D, you have 12 modes. So this shows you the transverse modes in X and Y. And so there's anything from the center of mass mode, like you saw there, that's an axial one actually, along the axis of the ion string. These are transverse ones, transverse to the ion string. You see center of mass mode, rocking mode, bending mode, and then in this case, the last one there is a zigzag mode that I'm going to talk about more in a second. So this set of modes, you can actually couple to all of them and enhance the speed and use it as a resource for both enhancing the speed of the gates as well as their fidelity, making them more robust to noise. So they are, through coherent control, really an added design resource if you can couple to all of them in a controlled manner. So typical gate fidelities, again, if you have two ions or in a small string, you can exceed quantum, typical quantum error correction thresholds, better than 93 nines of fidelity have been achieved. If you have longer strings, the gates are a bit slower, but and the fidelities are a bit lower. Okay, so with these gates, you can think about doing algorithms, but I want to think more generally about entanglement and quantum state engineering in a trapped ion system. So just to think more globally, there's a number of ways that you can generate entanglement and types of entanglement that you can generate in trapped ion, in a trapped ion system. So just to give you two examples, and in particular, I'm focusing on what are called Schrodinger cat type states. And so the first one is historically quite important. So these spin-dependent forces that I've mentioned to you, you can use to create spin motion entangled states, Schrodinger cat states. So entanglement between the internal spin of the ion, a single ion, and its motion in the trap, in fact, coherent motion in the trap. And so using these spin-dependent forces, you can have spin down, for example, at an instantaneous point being somewhere to the left in the trap, whereas if the ion is in spin up, it's to the right, and it's a superposition of these, in fact. So this is a paper actually from 1996. This picture is from Dave Wineland's Nobel lecture, sort of one of the key aspects of, or one of the highlighted features of his Nobel Prize. So related states to the spin motion cat states are purely in the spin sector, purely superpositions. They're really cat states in essence, but just of the spins of a set of ions. So I have that in the bottom picture there. All spin down plus a superposition with all spin up for n numbers of ions. These are often called generalized GHZ states. And so this, I have one particular experiment just to give you some numbers. So that's already a little bit old, but circa 2011, it's possible to push this up to 14 superpositions of 14 ions. These are some of the most sensitive entangled states that you can create, sensitive to environmental noise. So so 14 pushes the limit. I'm not actually sure what the current state is. Can't remember. Okay, so this is my little segue. So everything I've told you about, in particular, thinking about entanglement here. So whether you're creating superpositions of spin, you can think about that as sort of in the bottom there's a paradigm or for algorithms, quantum computation, or above here, spin motion cat states. All of these are essentially engineered entanglement, where you're engineering the forces, or you're engineering the interactions between the spins to generate effective spin-spin interactions by manipulating with lasers the spin and motion. So what I want to talk about now, and so in the focus of the remainder of the talk, is to something we've been working on, which is looking at an intrinsic, or trying to implement an intrinsic source of entanglement, taking advantage of a phase transition in a trapped ion system. So the difference here is, rather than engineer it, we want to try and take advantage of something that's very natural to the ion trap system. So, so a little, by way of a little bit of introduction, what I'm talking about here actually is structural phase transitions in a trapped ion system. And I'll get to explaining the quantum properties towards the end here. So this actually goes right back to even pre-trapping of individual atoms. So this is a little gallery of ion crystals in Paul, actually penning traps. Over on the left, you can actually see microparticles. So they're, I think they're aluminum particles actually. In the middle there, you see the first images of single laser cooled ions that have been crystallized. So really, the advent of laser cooling allowed these crystals to be observed. These are really essentially Wigner ion crystals. So when you think about Wigner crystals, you think about crystals of individual electrons. These are Wigner ion crystals. So some of these 2D ones in penning traps, you can see forming disk crystals with hexagonal structure. It'd be quite dramatic. The ones I want to focus on are still in a linear Paul trap. And down at the bottom, you can see, I'm talking a lot about is the linear to zigzag transition, going from a single linear structure to a 2D structure. Actually, it's just one of a whole hierarchy of structural transitions where if you continue, for example, to change the density of the ions in the trap, it will evolve from linear to zigzag to interwoven helices, so something like DNA structure, and so on and so forth. So these are all essentially, you can consider them classical structural transitions. These ions are not in the ground state. They are laser cooled, but they still have quite a bit of thermal motion. So just to give you, show you how this transition actually looks like. So there's a picture of a linear trap, my lab here at SFU. So the way we drive this transition actually is for a given number of ions, we will relax the transverse confinement of the trap. When you weaken it, it becomes energetically favorable to go from a 1D linear to a 2D zigzag configuration. So for something like 40 or 50 ions, you start linear. You can see this in a little animated GIF. And at the center is where you first form this zigzag structure. So because the ion crystal has non-uniform density, the transition happens first at the center where the density is highest. So although this is a small mesoscopic system, finite n, unlike what you might consider, say, in the thermodynamic limits in condensed matter, can nevertheless talk about this type of system having an order parameter, which is simply the size of the zigzag structure associated with the transition. And you can even draw a phase diagram. So just kind of summarizing, there's quite a bit of work that's been done. We've been involved in some of it and looking at this transition. So I have temperature on the left and trap aspect ratio that's associated with weakening of the transverse direction on the bottom there. And so classically, you can cross from linear to zigzag by either changing the temperature, it's not actually been observed yet, or classically at finite temperature crossing from right to left. So a lot of the interest in this transition is it's actually a second order phase transition. There's nonlinearity in the potential, which I'll show you in a second, and it can lead to interesting behavior. For example, topological kink defect formation. I'll show you a quick slide of this, just an example of classical dynamics that you can see in this circumstance. Where I want to spend most of my time focusing is after these initial experiments, we got interested in trying to see for the first time if it's possible to see the quantum version of this transition. And in particular, if we cross this transition, can we see superpositions of two structures, of two zigzag ion crystal structures? Okay, so just a little example of some of the things that can be done so classically. So as you cross this transition, if you have a large enough crystal and if you cross quickly enough, you'll actually form different domains of zig or zag structure with the boundaries between those domains corresponding to topological defects that are called kinks in this case. So you see an example there of a fast quench. We have 3 domains and 2 kinks, and a zoom in of showing the displaced ion position in the crystal. at the boundary between those two domains, the red and blue. So the interest in doing this actually was to understand the formation of those domains and to try and verify what's called the Kibble-Zurich mechanism for understanding the scaling and how those are formed relative to the quench time. I won't talk much about that, but I do want to just point out that what we're really studying here is these domain structures are, you can think of them as relics of frozen in thermal fluctuations. As you cross the transition, they get frozen in, and then you can see them in this domain structure. What we're interested in, or what we got interested in after this, is to really try and see if we could see effects of quantum fluctuations. So understanding this transition in the ground state motion. So here's a little bit, just a motivation for that. So if you imagine there's an ion trap and you have a zigzag structure. So classically, you would expect to see one or the other. What we're after, if you start in the ground state and cross this transition and remain in the ground state, you should form a superposition of those two structures. So, exactly what we'd like to see. So for 3 ions, you see zig, superposition of zig or zag, but particularly we'd like to see how far we can push this in terms of numbers of ions. So we think of this really as, given that we're literally provided with this phase transition with the ions laser cooled in the trap. So we think of it as an intrinsic source of entangled states, so of structures. And our goal experimentally has been to see if we can get sufficient control of this system to be able to prepare these superpositions of zig or zag. These are Schrodinger cat states, actually, just like I mentioned before, but in this case of structures. Those two states are really superposition, or the state that I'm showing you there is really the superposition of left and right in the double well, where left corresponds to zig and right corresponds to zag. And just to give you a feeling for numbers, when you have a double well, and if you were to start on one side, if there's the barrier is sufficiently small, you'll tunnel across. And that tunnel splitting actually is, or that tunneling frequency corresponds to the splitting between the ground and the first excited state. And so in this system, it's small compared to typical frequencies of an ion trap, but it's not very small. It's 3 kilohertz. So it gives you an idea of typical size scales. I like to think about these systems as a mesoscopic version of your good old ammonia molecule that tunnels between its 2 umbrella states. They call it mesoscopic because this is 100 nanometers size, more than 100 times larger, significantly larger than the size of the molecule, so mesoscopic. All right, so I'll finish actually. So in motivation that we're partly interested in this understanding this phase transition because it potentially provides a way to, through understanding its decoherence as a in-situ electric field noise sensor. So we're particularly interested in the applications of this system. So one extra piece of theory that's really important is to talk about the mode structures you cross this transition. And it helps to really understand properly how we think about the double well and what we'll use for observing the transition and where we'll be using spectroscopy. So from a mode perspective, what's really going on when you cross this transition. So I'm showing you a picture for 4 ions there and 4 axial and 4 transverse modes. So just thinking in 2D, what's really happening when you cross the transition is one of the modes, the zigzag, transverse zigzag mode, is going to 0 frequency. What that means is you get a dynamical instability in the system at that point when it goes to 0 frequency. fluctuations in that mode grow, and that leads to they form ultimately, they act as the seeds for the crystal structure. So this, when you have structural transitions with the mode going to zero, that's a well-known aspect of structural transitions in condensed matter, and it has this mode is often called a soft mode because it softens, it goes to zero frequency at the transition. If you write down an effective potential for that zigzag mode near the critical point, so I have a simple equation here that shows a quadratic and a quartic term. So it's a nonlinear potential, and the quadratic term, you see alpha squared minus alpha c squared, that's the trap aspect ratio. At the critical point, that goes to zero. The small oscillation frequency vanishes at that point. Classical small oscillation frequency vanishes. So that's this notion of the frequency going to zero. But when you have a 2-4 potential like that, that it is, if you plot it, that is ultimately a tunable intrinsic double well. So when that term that's quadratic is positive, it dominates. On the linear side, you have a single well. When it goes negative, you form a double well on the zigzag side. So this double well potential, is characteristic of a second order phase transition if it's in an ideal case fits symmetric. So thinking about this from a mode structure point, what really we're doing here, what we want to do to work with this transition in the quantum limit, we want to manipulate the zigzag mode, starting with it in the ground state. So we'll ground state cool it on the linear side and transport the system across the transition. If we do it adiabatically, we should remain in the ground state, assuming we have good enough coherence. So this is really, from that perspective, this experiment is really all about quantum manipulation of the vibrations of an ion crystal, one in particular, in the quantum limit. So not sure what happened here. It's a bit odd. So something just shifted. So just fix this second. What that is. So just a quick points about the notion of this transition in the quantum limit. So I already talked about this before, that if you have an inhomogeneous density, that leads to inhomogeneous mode structure and a transition. So the superpositions that we might hope to see will have some different participation of the ions, primarily at the center. But one point I want to make actually is for these finite systems, if you're more familiar with condensed matter systems, these finite N systems, there's a significant energy gap to the next excitation, the next mode excitation. What that means is that that acts to suppress the spatial fluctuations of the order parameter. We don't expect in this quantum regime for our experiment and the given number of ions we use to form domains, for example. So said a little more formally, the correlation length of our system is much larger than the system size. So there's some related theory. So just point out if you're interested, that is associated with Ising systems. So this paper from Zurich in 2006. So you see this gap to the next mode, which if you go to the thermodynamic limit of large N, vanishes. But at finite N, that's a finite gap. So we really expect, really what we're not really looking at quantum fluctuations with spatial variations when we cross this transition. We really essentially have one large molecule where we might expect to see superpositions between these two structures. Okay, so I have more or less one slide on some of our enabling technologies. So over the years, we've had to develop a lot of new technologies to be able to realize this system. It pushes in directions that aren't typical for a trapped ion system. I had to develop some new technologies. In addition to the experiment, it's really been soup to nuts. We've had to do a lot of we've done all of our own theory actually, just because this system really is different than what you typically look at for quantum computing with a set of linearized modes. So as far as the technologies are concerned, we have we've developed cooling. I'll talk about that in one quick slide, where you can cool efficiently and simply a whole ion crystal in all three N modes to within a few quanta of their ground state. We've had particularly to focus on high stability ion trap technology. In order to be able to see and control this transition, we need, approaching few parts per million over 100 seconds of stability, done through passive active stability stabilization techniques. We have individual addressing with optical tweezers, such that we can control the potential with optical dipole forces focused on a single ion. And most importantly, everything we do in terms of interpreting the system is done with spectroscopy. So these Raman transitions. So this is for 4 ions. Here's a spectrum I'm showing you here. So I was mentioning really everything about understanding the transition comes from studying the zigzag mode. It tells us about motional population, whether in the ground state, coherence, as well as the actually identifying the transition. The center of mass mode actually allows us to calibrate the trap, and that's our control parameter. So everything from spectroscopy is obtained from spectroscopy, both the control parameter and the readout. Okay, so just very quickly, so we developed a technique that has been known for 30 years, actually, been used for 30 years in neutrals. So Sisyphus cooling that had, till we did it, had not been achieved in trapped ions in 3D. So, and we found that it works quite well, actually. There were certain reasons why people thought it wouldn't work, found a way around those. And we're able to cool, so this shows a picture of that. You see a whole bunch of points. They're all the different modes and the N bar. So that's at mean number of phonons in the mode, assuming it's a thermal distribution, all below about 2. So we start at 20 or 30 with Doppler cooling. We can bring all of these modes close to the ground state. And then we finish using a little bit of what's called ground state sideband cooling to bring a select number of modes within, with 90% occupation or more of in the ground state. And so, while we developed this for our particular experiment, it's been used and continue to be used in other systems or other groups around the world. So it's particularly useful for cooling large ion strings for simulations. And other applications. Okay, so we start with a cooled zigzag mode. So in the ground state, we ramp the trap to cross the transition. And then we measure the frequency of the mode. So measuring the frequency of the mode, like you see in the bottom there, is we use Raman transitions. I'm not showing the whole complication, but we're really driving transitions between the different motional modes to read out their frequencies. And you see this characteristic drop to 0 at the transition. So we measure both the first and the second sideband. So we can extract the energy spacing of the first and the second quantized energy levels. And the first thing I'll point out about this, so you see this, we can identify the transition. It's a very sharp transition within the system. So this is 20 kilohertz. We have typically a 700 kilohertz or 800 kilohertz trap. So the full range that you're seeing here is 5%. The actual transition happens over about 100 hertz or something like that. We need extraordinary stability in this system to be able to see this, but you can see it's quite clean. just to show you how clean it is. So we've been able to measure things for the first time that haven't been seen before or been able to be measured simply because we have very good stability and can achieve good ground state cooling of the system. So as an example of that, we actually see a shift in the critical point by about 3 kilohertz, 0.5%. So it's a shift up. It's a purely classical effect, but this is, and it's due to the micromotion in the RF trap. So when you have a zigzag mode, when the ions move off of the RF null, where there's no radio frequency amplitude, they dither or modulate, and that leads to a correction in the Coulomb interactions between them, leads to a shift in the critical point by about 0.5%. So it's an interesting effect. Purely classical, but this is just to give you an idea. I'm zooming in here already on the transition. You can get an idea of how sharp it is and how stable it is. This data was accumulated in the way that we do it over about 10 or 15 hours. So just to give you an idea of how some of the things we worry about at the level of stability that we're working with. So in order to see this transition, we need 100 ppm level stability. And just to give you a couple examples of sources of noise at that level up on the trap potential. I have a little sketch of an ion trap. You see 4 rods, some UV light coming in that we use to address the ions. Stray light can hit ceramic and create patch potentials due to photocharging. Even though the vacuum is good, it's still possible to get adsorbates on the rods. Both of these can affect the transition at that level. So as an example, we ended up with some significant adsorbates on the rods, made the transition wander around over minutes. It was dramatic. And so some of the things we worry about is, very basic in situ surface science, actually, where we actually actively heat the electrodes using a powerful laser in such a way that we don't destroy the electrodes. Basically removing the molecular adsorbates off the surface in order to get a stable transition. Okay, so this is one of the key plots I want to show you. So this is now zoomed in right to the transition. So remember, we have about 1 megahertz trap frequency. You see, this is now on the order of a few hundred hertz. That's where the transition happens. You see the first and second sidebands that tell you the energy levels between the ground and the first and second excited states. Red points, blue points are data. So again, 15 hours of time. Pretty good fit to a quantum model for energy levels. And in the green, you have classical small oscillations. So there's clearly a difference between the quantum and the classical. One of the points that I want to make here is you only really see a distinction between classical and quantum when you're below 100 hertz of the transition. So again, that's, we're operating at 10, 100 parts per million here shifts between those points in order to see this effect. And keeping that stable over a few hours, just to give you some more idea of that. The points here, we're actually changing a DC voltage on the order of millivolts, even when we have almost a kilovolt present in the ion trap. It's oscillating at 30 megahertz. So in some way, it's actually surprising that we can get this level of stability. So the structure of those energy levels allows us to understand the shape of the double well close to the transition. Said in another way, it allows us to understand the nature of the phase transition. And in particular, generalizing from typically discussed in ion trap context and some of the early proposals here, we have to consider bias terms. So there's linear cubic bias terms. So in a typical Landau theory for a phase transition, a cubic would take you from a second order to a first order phase transition, for example. So that's what I mean when I talk about nature of the phase transition. So the The C1 and C3 here, we actually include in a fit to these energy levels in order to be able to extract what their values are. From a simple perspective, or you can get a quick idea of what's going on in the fit. The red line there shows a frequency that approaches zero frequency. So as a double well forms and the barrier rises, you expect the degeneracy of the two lowest levels to go to zero. So if those levels don't go to zero, that indicates there's a bias. There's more to it than that. As the depending on the bias, there's different coupling between the different levels because of overlap between the wave functions, and that affects the transition strength that we can also extract. So I'm not showing that here, but we include those things in our calculations. And what we can extract from this situation is that this is for 5 ions. So these are actual fits that I'm showing you here. So at the optimum tunneling point, which is about 100 hertz below the transition, just when the first 2 levels are below the barrier, we have a pretty good bias, better than, it's a few parts in 10⁻⁷. And we have to reach that level in order to get decently symmetric wave functions. You know, so even at that level, our bias and our wave functions, you can actually see a slight bias in the ground state. So we have a symmetry that's left-right symmetry of about 0.6, so 0.5, half would be ideal. If you were an order of magnitude, you would have enough bias that the ground state would be either all right or all left, and you couldn't possibly see any kind of tunneling. So so I'll talk a little bit more about that bias in a second, but I just want to show you some of the other features that we can get in looking at this system, all from spectroscopy. So this is a very different system than linearized harmonic oscillator modes that you typically encounter when you're thinking about quantum manipulation and trapped ions. This is really a nonlinear oscillator here at the transition. There's that quartic term. And because of that, from the spectroscopy, we can get a direct readout, essentially, of the motional population distribution in the quantum levels. So, for example, before you hit the double well, you see I have a somewhat quartic potential. That's the top there. And for each of the transitions, 0, 1, 1, 2, their frequency resolved. So you can literally read out what the initial population is, 0, 1, 2, 3, 4 states. And that's what we show here on the right is the population distribution of the different quantum levels. When you form a double well, it's a little more complicated, but we can also extract populations. And what we use those for is to see, as we cross the transition, what is the ground state population as we cross. So we'd like to remain majority populated in the ground state. We do at the optimum tunneling point, have about 60% in the ground state. We know how we can do better, actually, just because of the adiabaticity. So that's the picture I show you on the left there. So you come from the linear side, we're in the ground state, that's the red there. And then the population, even on the other side in the double well, is still majority populated in the ground state. And then you see that it approaches half there. That's because we break adiabaticity at some point as these energy levels become too small. Splitting becomes too small compared to some characteristic frequency associated with our ramp. Okay, so one little quick thing, just circling back, give you a feeling we can vary the number of ions in our transition. And so going from 3 to 4 to 5, I'm showing here on the left the first sideband. And so you see as you go from 3 to 4 to 5, you approach 0 frequencies, you cross the transition. So that's the degeneracy associated with symmetric double well. And from these shapes, we can extract what the potential looks like. These are actual fits. So for 3 ions, there's actually there's nothing different, much different about the trap. It's in the same trap, but for 3 ions, the bias is quite large. It's so large that we don't even form a double well in the vicinity. For 4 ions, we form a heavily biased double well. And for 5, we already have symmetry, a pretty decent symmetry in the double well. The essence of what's going on here, it's actually in some way, it's a little surprising that things converge so quickly. So we have to understand that. So as you go from 3 to 4 to 5, what's going on here is that as you move to higher numbers of ions, the ion crystal becomes better symmetry protected from imperfections in the trap electrode structure. So when I was first getting into this, or thinking about this experiment, I knew that if you had an even number of ions, it would be very well symmetry protected compared to odd ones. This was surprising to me that you go from 3, 4, 5, it very rapidly converges to a good symmetric trap. Look at the numbers here, 10 to the minus 5, 10 to the minus 6, 10 to the minus 7 symmetry or bias coefficients. Those are very small numbers when you think that the tolerances on our mechanically assembled trap are up to 10% actually. So it's telling you about, you know, how good this system can be in spite of imperfections in the system. So that's one of those good technical things where, you know, if it works in spite of problems in practice, that's actually tends to be a good idea. Okay, so just about finished here, actually. So I just want to give you a couple of quick slides to tell you about some of the things that we're planning to do. So on one, this sharp transition we'd like to use for electric field noise sensing. The transition is so sharp, it allows us to understand fluctuations of electric fields within the trap. With considerable enhancement, we can study this in different ways using absorption or coherence measurements. And we'd like to take and put this system into different types of advanced ion traps, even cryogenic environments, to use it as a electric field noise sensor. It's also broadband. With just small changes in voltage, we can probe different frequencies. So I think I just realized that time is actually short. I'm going to cut to one quick slide and then finish. So I've talked all about the mode here and superpositions of structures. I just want to point out, we haven't really pursued this much, but you can use this structure and the nonlinearity, the potential to generate in simple single-step ways, multi-spin entangled states. So if we go on the 0-1 state, which is frequency resolved from the upper ones, and you drive what is a simple transition, seemingly, it's effectively a 2-level system. The effective spin you generate is something close to a Dickey state, actually. So a Dickey state is actually an equal superposition of a given number of excitations. Here, we don't have quite an equal number of superpositions. We haven't done this at this point, but we can, so haven't really compared carefully how much advantage there is compared to what other people do. Yeah, perhaps in the future we'll assess coherence. One of the advantages is we don't require individual addressing to prepare these states like you would, for example, in a typical system. Okay, so in conclusion, so we've extended this linear zigzag transition in the quantum regime, demonstrated some key ingredients for double well interferometry with ions, and we're going to do some coherence characterizations, look at some applications for electric field noise sensing. That's it for me. So I'll leave here on the slide the people that did this and take any questions if you like. So, all right. So the people in START are those that contributed to the work that I was showing you here in my group. All right. Thanks a lot.
Hey, any question from the audience from Zoom side?
The bear is real, by the way, but you probably knew that already.
Oh, really?
I didn't Photoshop it.
You take this photo?
I didn't take it, but it's happened last year. Somebody got a kind of a shot of it, and it's perfect for advertising. I think it's perfect for advertising. All right.
thank you for your insight. There is actually a modes approaching zero in your chart. One of those modes. Could this be attributed to the actually the Polish current of the inside your model?
Oh, sir. Well. Oh, I see. So you're actually asking for corrections to the excitation structure if you have domains, or you mean the actual formation?
So I'm asking whether there is a, to Polish distinct phases inside your model in which you can expect to see some zero modes.
Oh, so in so
in fact, about some domain modes and some sites.
Yeah.
One chain.
So so if you have these domain structures, they can be stable, and actually you can have localized excitations on those. And in fact, there's proposals to look at quantum, actually use those to store quantum information. But it's really, so I don't the types of, so I've looked at the theory to understand, as you cross this transition, freeze out times in the quantum case, and formation of domains. That really doesn't happen for these low end states. I have not considered theory of what happens if you have these structures in there, and in the quantum dynamics of them, if that's what you're asking about. Yeah. So.
Any other question? I'm interested in the Dickey state. So why non-linearity can say enhance the generation of the Dickey state?
Oh, so it's actually so it's really because they're frequency resolved. So if you have a typical harmonic oscillator, so if you couple to the first excited state, you'll then, and you leave on the global interaction, you'll continue to excite and all the way up to, n phonons of interaction. So they have a very different state. So here, we turn down the power such that the 0 to 1 state is well resolved from 1 to 2. So it's really a closed level of system. So the way that Dickey states are actually done for traptines is you prepare the 1 state and then you drive a red sideband back, and so there's nowhere else to go. So it's very similar. You have this effective 2-level system that leads to these Dickey type states. So yeah, it's really the nonlinearity is really what's giving you the frequency resolution of these, or the frequency separation between the latter levels.
The advantage for it is that the qubits are coupled to the mode in some parts of interaction, but now the mode itself is non-linear, so that way you can.
Yeah, that's right.
I see.
Yeah. So we don't have individual addressing here. This is all global illumination. So
but just single driver you have it.
Yeah.
Okay, any other questions? Any other question from the Zoom side?
Yeah, I have a question.
Oh, Aaron, hi.
Hi, Errol.
Hi, Paul. Great talk. Really enjoyed it. I kind of will come back to the beginning. These ions, do they have a magnetic moment?
They do, yes.
So can you address them with the polarization of the light? Let's say circular polarized left and right circular polarized light.
Yes.
Are you using it?
We are, yeah. So you get these spin-dependent forces. So we use the polarization also for state preparation. So you can do optical pumping using polar. Yeah. So in this case, it's actually, in this case, we don't actually, so we have good polarization, but in other ion trap systems, use polarization for good state preparation with optical pumping. So yes, you certainly use it all over the place. These Raman transitions, we have very specific polarizations, even for the 2-photon transitions. The one thing
Because
with
it's used like in a circular dichroism. You can polarize, let's say, right or left polarization. You can excite up or down spins, and in this way you can see population of each.
Yes, yes. So the one thing that we don't do in that case is it's so in terms of dichroism, you have a single spin. So you know, if you have a bulk medium, you can pass the light through and, like you say, see some rotation of the polarization of light. The trouble is if you just have these in free space and you're putting the laser in, a single atom isn't really enough unless you do something extra to, you know, provide a large rotation of the laser. We're really mostly looking at fluorescence directly, you know, of the ion. Yeah, so I did some of that stuff in my earlier life with neutral atoms. So you have a cloud, a VEC cloud that you can tune and then see, you know, phase shifts. So some of the things you're talking about, but for single ions, unless maybe you have it in a cavity, you typically don't look at the effect of the ion on the laser. It's usually, you know, fluorescence.
Thank you.
Okay, so we are a bit overrun, but some nice people again for the exciting talk.
Thank you.
So the next quantum physics seminar will be on the 11th of July, and the speaker will be Lucas Kropowski from QBC. So hope to see you again. Thank you.